Hello everyone, today we'll talk about Chapter 1, Introduction to Chemistry. So these are easy topics that we'll talk about today, and hopefully it's going to give us a quick and easy introduction to the course and the expectation and what are you guys going to experience through the next few months. So today we'll talk about measurements in the metric system. So this is pretty essential to our work, especially in the lab, the first few labs, and even actually goes beyond that when we do measurements. And we also talk about the metric system and how the metric system is applied when it comes to measurements. We will also discuss precision and accuracy, and although these two terms are interchangeably used in our daily life, but they mean two different things, and we'll talk about that more in details. And then we'll address significant figures and how we can use significant figures when we do measurements and why the significant figures is important, and also how we can use the rules of significant figures when it comes to mathematical operations. And then we'll finish off with scientific notations. Before getting into any of this, this is really a generic scientific method diagram, and this is how all scientific methods usually. This is the route that the scientific method follows. And any scientific discovery, regardless if it is a chemistry related or not chemistry related, usually goes through this cycle of life, which is an observation later followed by hypothesis, and the hypothesis then is examined by an experiment. Now, obviously, the experiment can accept two outcomes, either a failing experiment or a successful experiment. If it's a successful experiment, that's obviously the ultimate goal for any scientist that later would be published and then goes into an application at the end. However, sometimes it fails, and scientists, in many times, they actually face failed experiment more than a successful experiment. But even with a failed experiment, there is actually a great deal of advantages because in many times, in many cases, during a failed experiment, you can make some other observation that can really be intriguing and can open the door to other scientific discoveries. And in the meantime, even if that doesn't happen, you are going to acquire more skills that can really be beneficial, in later experiences. So even in our lab, for example, there are days when you will be getting a lab report. Not the best way that you would like to, but I guarantee you, in every day that when you go home, you will be taking some, and you will be learning some good skills by the time you finish that lab. So. Although the ultimate goal is to get a 100 points or 15 points of the lab report, that's yes. But even if you don't get that one, there is some advantages that we take from the lab on top of getting good reports. Okay, so science. Let's talk about measurements. So science, obviously, it's based on measurements. I mean, without measurements, how can we really examine and how can we tell? Quantities and how can we measure success or failing even when it comes to experiments. So measurements goes to the core of science in general. So measurements, it constitutes of two different elements. First, the value, which is a quantitative description that includes both. So the value is constitute the number and the unit. So the number in this case, for example, it's 100 meters. So the meter basically indicates to us that it is a distance. So the unit, it does help us to determine if it is a distance, if it is a mass, if it is a temperature, so on and so forth. So the value, which is the measurement, the value for the measurements, it constitutes the number and the unit. The units are the quantities defined by standards that people agree upon. So the scientific community, scientists all across the world, they agree on certain units or certain unit system that everyone follows. So it's easy. So data are easy to understand and interpret, regardless of where that experiment, for example, has taken place. Okay, so a number without a unit, it really doesn't mean anything. If you say 100, you're talking about a distance. Is it 100 centimeters? Is it 100 kilometers? Is it 100 miles? So the units, it really tells exactly what are you trying to measure and what are you trying to what are you trying to say basically. So in the exam, if you, for example, Do your calculation, and then at the end you just report the number without unit. I surely will be deducting points. So just to keep that thought in mind, unit is very important. So some units can be very long. So obviously we don't use the unit name, we use abbreviation for that. So this table here, for example, it tells you exactly the length. We measure it by unit. Oh, I'm sorry, we measure it by the meter, and this is the base unit. The reason why we call it the base unit, because later on there will be some derived units out of the meter to measure the length. The abbreviation for the meter is small m, as you see. The mass is measured by a gram, and it's a small g. Time is a second, small s. Temperature is a Kelvin, and we use K. A scientist or a chemist, and you will see also in many of our calculations, we use most of the times Kelvin. I mean, sometimes we use Celsius, but most of the times it's Kelvin. When it comes to amount of substance, we use mole or MOL, and that really helps us to report how much exactly when it comes to or how many units or what's the amount of the count of substance in a small tiny amounts. In other words, for molecules and atoms, so on and so forth. Okay, volume is liter, and the abbreviation is a capital or an uppercase L. Okay. So let's start with the volume. So the volume is also known as a derived unit. And the reason why we call it derived unit, that you can measure the volume of a content by just measuring the volume of its container, correct? So if you have a cube, for example, and you fill that cube with water, you can essentially just measure the volume by measuring the volume of the cube itself, because obviously the liquid will occupy the shape or the volume of its container. So in this case, if you want to measure the volume of the cube, so it's 1 meter in width, 1 meter in length, and 1 meter in height. So you can multiply the length by width by the height, and you can multiply all that together, and you'll get the volume of the cube or the volume of the liquid itself. So that's why it's called also as a derived unit. For example, the 1 liter, we can also, so the 1 liter is 10 to the power negative 3 of the cubic meter. And we'll talk about this surely more in details. Or 10 to the power 3 or 1,000 of a liter equals 1 cubic meter. You might be also familiar with possibly cubic centimeter, right? I don't know if you've done any biology, but you might have seen something like this with a superscript 3. So this is a cubic centimeter, okay? Or it's also equal to a milliliter, okay? So if you ever looked at a syringe, usually it's either cubic centimeter, or they also refer to it as cc, as a cubic centimeter. So that's a milliliter, okay? So that's what derived unit for the volume means. So these are the metric prefixes, and I think one of the really most powerful advantages that we have from the metric system, that you can use a certain factor to convert between larger unit to a smaller unit, regardless if you're measuring for mass, for distance, or for volume. So for example, you can use the 10 to the power 3 or 1,000 if you want to convert from the kilometer or from the kilometer to the meter. So remember, the base unit here, this is either a meter or a liter or a gram or a second, okay? So these are our base unit in the center. You can go right or left. Small unit, so this is large unit, right? And this is a smaller unit. So if you're going for example, from the kilometer to the meter, you'll have to multiply by 1,000. So you can just multiply by a factor of 1,000 and it'll get a meter. You can multiply by a factor of 1,000,000, 10 to the power 6, and you get a mega meter, okay? Right? Because we have 2 factors of 1,000, so it's 1,000,000. Or you can multiply by 10 to the power 9 or 1,000,000,000, and you'll get a gigameter or a gigaliter or gigasecond, so on and so forth. Okay. Now, if you go from a milliliter to the base unit, which is let's talk about the liter since we said milliliter, then you'll have to multiply by 10 to the power negative 3, or you can divide by 1,000. So your unit will be here, and then you'll divide by 1,000. So going from a larger unit to a smaller unit, you multiply. Going from a smaller to large, you'll have to divide by that factor. And that same rule applies for the liter, for the meter, for the gram, and for the second. Okay. So this scale, I'm going to try to give it to you at least in the first exam, so you guys are able to utilize it when you do conversions. But I think by our second or third exam, I expect everybody to be really familiar with this. Be able to convert from a meter to a kilometer, or from a centimeter to from a gram to a kilogram, or to the megagram, without even looking at this. So on the first exam, you'll have it just to give you an advantage, but later on, you should all be familiar with this. So when it comes to metric prefixes, just like how we looked at the scale here, so these are the units that are larger than the base unit, right? Like the gigagram, the mega, the kilo, so on and so forth. The abbreviation, we call it G, capital G, capital M, and small k. So for example, if you're talking about a mega, if you're talking about a gigagram, so this will be a capital G, a small g, or capital M, uppercase M, a small case g, and then a small case g right here. Okay. Same thing for the centimeter, for the milli, the micro, and the nano. Okay, so the centi maybe, so the centimeter is not really mentioned up here, but the centimeter is 10 to the power, let's see. It's actually right here, 10 to the power negative 2. Okay, so this is 10 to the power negative 2 centimeter. It falls right in between the milliliter, between the milli and the base unit. Okay, so let's go back to the abbreviation. So the milli is a small m, and then if you're saying milliliter, so for example, the liter, we use the uppercase L, so it will be an ml. The micro, this is not U, rather this is mu, the Roman letter. So for this one, it's a microliter, or a micrometer, or a microgram. So basically what we are doing is we're combining the abbreviation of the base unit, which is we talked about in slide number 2, and with the abbreviation of the small unit. All these conversion factors, these are basically the same thing from this spectrum that you will be given in the first exam, as I said, but you should be all familiar with at the same time. So the point from these 2 slides, or the few slides to come, not obviously to memorize pictures, but just to give you a perspective into conversions. That's number 1, between 2 measurement system, and also exactly to give you a good way to have some kind of analogy to something that we experience through our daily life. So you can basically make sense when I say a meter, or when I say a foot, so on and so forth. So for example, every 1 mile, or every 1 kilometer is 0.6214 of the mile. So the mile is the larger unit, and the kilometer is the small unit. Okay, the mile equal 1.609 kilometer. So obviously, if you have driven to the campus, to the Gateway campus, if you came from West Haven, for example, so that would be 6 miles. If you want to figure how many miles, how many kilometers will be, then you'll have to multiply that 6 miles with 1.6 kilometers, okay, to find out how many kilometers you have driven. So that's when it comes to miles and distance. When it comes to meter and feet, so a meter usually is the distance between the doorknob and the bottom of the door, or that would be basically a 3 feet also. Every 1 meter equals 3.281 foot. Okay, and the kilometer and the meter, these are all metric system, by the way, or the SI system also. So when it comes to centimeter and millimeter, so the millimeter is usually the width of the nail of the paper clip. The centimeter, however, is the width of your nail, fingernail. So that would be a centimeter, and these are the conversions. Okay. So when it comes to range of lengths, and again here we are using first the scientific notation, which we'll talk about later, and you will see how it is really helpful to know the scientific notation, especially when it comes to displaying large numbers, as you see here. And also the metric system, because I can't even imagine using something other than the metric system to, for example, um, propose or try to report the number of boundaries of the universe. Okay, um, so it's 10 to the power 30, for example. And then you have the diameter of the sun, which is 10 to the power 9 of the meter. Okay, so and you can see the difference and the relative difference between every single measurement of these. So the metric system allows us, for example, to measure out the diameter of a proton, and at the same time, it allows us to measure out or expect the distance, the boundaries of the universe. Okay. And you can see at the same time and compare like the hairline, the diameter of a hairline, which is 3 times 10 to the power negative 6 of the meter. The atom, which is something that we will look at and investigate heavily later on, 10 to the power negative 9 meter when it comes to the diameter of the atom. So that's what I would like you to learn from this. The volume, there are different measurements for the volume. Sometimes really the industry or the application. For example, we're used to get a gallon of milk. We're not used to get 3.4 liters, or 3.4 liters, of a milk. That's what we are used to get. Other measurement units also used for volume, like the fluid ounce or the FLOZ. I don't know if you ever looked into like the nail polish bottle. They will always use something like that. Every 1 milliliter is about 20 drops from a pipette. So at the lab, obviously you will be using. I know we'll be using pipettes at least during titration. So every 20 drops is going to be about a mil. A gallon, which is about 3.7 of the liter. It's also 4 quarts, approximately 4 quarts, and that would be basically the paint can if you go to Home Depot and get one of those. Now the small one, the big one. The quart is about 0.9464 of a liter, so it's almost a liter, but not quite a liter. And it's also 32 fluid ounce. Okay, so these basically just to give you an idea what is a gallon would look like, what is a liter would look like, and what is the relation between the liter and the fluid ounce, so on and so forth. I don't expect any of you to memorize any of these. If there's any conversions for those ones, I'm going to try to give you this so to make things a little bit easier. Okay, ranges of volume, and again, if you notice here that we're using a liter, so that's the SI system, and we're also using scientific notation. Without using these two tools, it's going to be pretty ridiculous to display these numbers, especially when it comes to something like the sun, for instance, which is 10 to the power 30 of a liter. So, and we can also measure something, the volume of a proton, which is 10 to the power negative 42. So something very small. Okay. So this is basically to establish and give you an idea and be able to establish a relation between, like small tiny objects like the proton and how much volume measurement that would have compared to something like the sun or the earth, for example. Let's talk about mass and weight. So although we use mass and weight in a two different, and we try to in many different ways in our daily lives, and we sometimes interchangeably use the mass and weight, and we're actually used to use the term weight more than mass, especially when it comes to measuring someone's weight or going to the store and getting like apples or getting getting tomatoes, so on and so forth. So we always deal with weight and not deal with mass. However, that's scientifically speaking, this is not quite correct, and we will see why that is. Let's talk about definitions first. When it comes to mass, mass is actually defined as a measure of the amount of a matter in an object. So if this might sound a little bit fancy, but basically what it means is it is the amount of an object. So whatever that material, whatever that matter contains, the amount of that material, it is considered the mass. Okay, the matter is anything that occupies a volume that has a mass, anything. And when we say anything, that could be the room that you're sitting in and listening to this lecture that has air that occupies everything in there in the room. That air will have a mass because it occupies that volume. The weight, however, of an object on Earth is a measure of the force of a gravitational attraction between the object and the Earth. So we're talking about attraction force between the gravitational forces of Earth. If we're talking about measuring a weight of a material on Earth, obviously, if talking about measuring that material on Moon, that would be different. On Mars, will be something else. We're talking about the Earth in this case. And because the gravitational attraction force of the Earth is different than any other um, planets and moons and space, so the weight will vary depending on when that matter or where that object is, depending on the gravitational force. Therefore, the mass of an object is the same no matter where that object is in the universe, but the weight depends on the gravity. Okay? So, if you look, let's talk about an astronaut, for example. So that person mass on Earth is 65 kilograms, right? Kg. While traveling to the moon, between Earth and the moon, that gravitational force obviously is a zero, right? Because if you look at if you look at astronauts in the International Space Station, for example, you'll see these folks floating, right? They never really sit on the chair. So that gravitational force is a zero. So the mass for that one, in this case, 65 kilograms. However, the weight will be a zero because when we are measuring the weight of an object, what we do is we multiply the mass the gravitational force. Oh, sorry. So I'll multiply the mass with the gravitational force, or g. Okay? Sometimes it's also referred to it as a acceleration. So going back to the Earth example, because the gravitational force on Earth is 9.9. Okay, so let's fix that one. So it's 9.8. 9.8. Sorry about that. Time, multiply that by 65 kilograms. The weight then will be 637 Newton. Okay, and that's a different unit for measurement, which is gram, which is meter per second square time the mass, which is kilogram. So that will be a Newton. When it comes to between Earth and the moon, as I said earlier, the gravitational force is a zero. So you multiply the zero by the 65, the weight will be a zero. On the moon, because the gravitational force is 1/6 of what it is on a planet Earth, so the mass will remain the same, which is 65 kilograms, right? Because the mass is not the gravitational force is not factored in when it comes to mass. However, the weight will be 106 Newton. So that's the difference between the mass and the weight. So when it comes to mass, for example, the 1 ounce, it's about 28.35 grams, or it's about the nickel. So if you weigh the nickel, will be about 28.35 grams. A 1 pound is 453 grams, or about 500, or 453, I'm sorry, and 1 kg, 1 kilograms will be 2.205 pounds. Okay. 1 megagram, remember this one, a capital M, uppercase M with a small case, with a lowercase g, that's a megagram, equals 1,000 kg, right? And that one also equals 1 ton. It's about it's the mass of a basketball team combined all together. Okay. And every 1 megagram mg right? Remember, this has to be an uppercase M because we do have a small case m, a lowercase m with a g. That's a milligram. This one is a megagram. So we need to draw a difference here, or a metric ton. Ranges of masses. We have something as tiny as small as the electron, which is 9.1096 times 10 to the power negative 28 grams, something very small and oftentimes is really becomes negligible when it comes to measuring the mass of an atom because it's very small. When it comes to the atom is 1.6735 10 to the power negative 24, so the atom is heavier than the electron. And the universe, it's 10 to the power 54 grams. Okay, so that's when it comes to mass, volume, and also the difference between mass and weight. Let's talk about temperature now. So temperature is defined as the measure of the average motion of particles in the system. So as these particles move within the system, temperature is generated, and this is what the temperature essentially means. A higher temperature means more movement, right? I think that makes total sense. So, for example, if you're boiling a kettle on a stove, for example, and you can see as you increase the temperature, the movement is increasing. So, higher temperature means more movement. When we try to measure the temperature of a specific medium, for example, we either use, we'll be using thermometers, but the units that we're using, it can be either Celsius, Fahrenheit, or Fahrenheit. We also use Kelvin, and we'll talk about Kelvin shortly. But when it comes to Celsius and Fahrenheit, they are not the same. They are not equal. So, for example, if you take a beaker and you put some ice cubes in there, and you put a thermometer that measures degree C, and a thermometer that measures degree Fahrenheit, you will see the degree Celsius will be measuring 0 degree C, right? Because that's the temperature of freezing of water. In the meantime, the degree Fahrenheit will be reading 32. If you were to boil that beaker and start increasing the temperature and bring that water to boiling point, you will see the temperature at and the thermometer that reads degree C is 100 degrees C, and the Fahrenheit it's 212 degree Fahrenheit. What this tells us that between the freezing point to boiling point of water on the degree on the thermometer that reads in a degree Celsius, there's 100 degree C or 100 degrees Celsius, correct? Going from 0 to 100. On the other hand, if you look at the degree Fahrenheit, we started with 32, and we reached 212 when it comes to the boiling point of water. So instead of having 100 degree, we have 180 degree Fahrenheit. What this tells us that the degree Celsius is not equal to the degree Fahrenheit. As a matter of fact, every 1 degree C equals 1.8 degree. Oh, sorry. Let's delete this one. Every 1 degree C equals 1.8 degree F. So degree Celsius is not equal to degree Fahrenheit. Degree Celsius, in fact, it is larger than the degree Fahrenheit. That's why when you're looking at the weather, for example, here in the U.S., obviously, all the metrology is being reported as all the metrologists that report the temperature at degree Celsius, degree Fahrenheit. So we see 85 degrees, 75 degrees. That would be a spring temperature, like a nice beautiful day. But at the same time, if you convert that to degrees Celsius, it will be 23 or 25 or something in that range. So the degree Celsius is larger in magnitude than the degree Fahrenheit. I would like you to keep that thought in mind. When it comes to the degree Kelvin, it's the temperature used by chemists. So chemists all the time use Kelvin in temperature, especially when it comes to measuring temperature for gases, for example, because the temperatures for gases can be very low. So we use Kelvin in this case. The 0 degree Kelvin is also known as the absolute zero, and it is the temperature at which there will be no movement, and it is the lowest temperature is being captured, and there's nothing below that. And Kelvin, Kelvin actually equals, and you'll get that also. You'll get that formula equals degree C plus 273. Now some books also use 0.15, which is fine. Okay, so whatever your temperature is, you'll have to add 273.15, and then you'll get the temperature in Kelvin. So the absolute Kelvin, when we say absolute Kelvin, or the temperature 0 Kelvin equals equals 0, I'm sorry, that means your degree C must be equal to negative 273.15, right? So in order to 273 will cancel out with the 273 to equal 0. So the absolute 0, in other words, also equal negative 273.5 degrees C. So you can imagine how low that temperature is. So it's very low. That's why Kelvin is used in reporting temperatures by chemists, because it allows reports very low temperatures. Okay. So if you put the degree Celsius thermometer next to the Kelvin, next to the Fahrenheit, these are the similarities or differences when it comes to every thermometer, and which every thermometer allows us to measure, and how the measurement will be done. So for instance, if you look at a degree C, the freezing point for water is 0 degrees C, and it also boils at 100 degrees C. So there are 100 units between 0, the freezing temperature of water, and the boiling temperature of water. When it comes to the Kelvin, the 0 degree for water, the freezing point for water is going to be 273.15, and the boiling point for water will be 273. So there are 100 units. So for every 1 Kelvin, so Kelvin and Celsius, they are equal to each other when it comes to degree. When it comes to 1 Kelvin equal to 1 Celsius. Okay. Fahrenheit versus Kelvin and Celsius, it is different, because as we said earlier, the freezing point for the Fahrenheit for water is 32. The boiling is 212. The difference is 180 units. So every 1 degree C equals 1.8 degree Fahrenheit. So that's in terms of temperature and measuring temperature, and the 3 different units that we use. Kelvin and Celsius probably are the ones that we will be using more frequently. Okay. Let's talk about precision and accuracy. So let's talk about precision and accuracy. And these two terms you're probably familiar with from our daily lives. We use them interchangeably, but they actually mean 2 different things when it comes to statistics and science in general. So what precision means, it describes how closely a series of measurements of the same object resembles to each other. Or how close they are to each other, regardless of how close they are from the true value of the measurements. When it comes to the accuracy, however, is the measurement's relationship to the property's true value. So let's put it this way. So precision, when you have a group of measurements that are done together in the same time, the relationship between each of those measurements to each other, regardless of how close those measurements to the true value of the measurements, this is called precision. So you might have something that has really high precision, but it has a very poor accuracy, because these measurements collectively, they were close to each other, but they were not close to the accurate value, to the true value. Accuracy, however, is when these measurements are close to the true value, or the relationship to the property's true value. So you can see where these, these 3 archers, they are close to each other, correct? But they are far from the center. They are far from the target. So those are high precision, but they are poor in accuracy. They are very low in accuracy because they don't really hit the target. Here in the center, this is the ideal case scenario where you have all the measurements close to each other. So this is high precision, and in the same time, they are high accuracy because they have hit the center target. On the other hand, if you see here, so those are the measurements where you have poor precision, right? Because the relationship to each other, they are really unrelated, hitting three different spots, and at the same time, they are really far off from hitting the target. So they are poor accuracy. Okay. So you might have something, as I said earlier, you might have something that has really high accuracy but poor precision because the values are scattered all over the place, but you have one measurements that actually hit the target. So that's a high accuracy. Um, for example, in the lab, um, so a group of four students, for example, they were doing the freezing point for water. So they three of them they were following the procedure incorrectly, making the same mistake. They will end up with the same value. So they could end up with, for example, a positive 5 degrees C for measuring the freezing point for water. So those three students, with their values, with their measurements, they will have a really high precision, but their experiment has a very poor accuracy because it's far off from the 0 degree freezing point, the true value of freezing point of water. Okay, hope that makes sense. All right, let's take an example and talk about precision and accuracy when it comes to using scales, analytical scales. So when it comes to using analytical scales, scales with high precision, it's always required because obviously it gives you a really reliable measurements. So when you look at the scale, for example, the scale with the glass windows right here. So this let's go scale number 1 and this is scale number 2. This one can measure to the 4 decimal, right? 1, 2, 3, 4 decimals, 4 digits beyond the decimal. So this can measure, that can give a really reliable measurements. In the same time here, when you look at this panel scale, you can see there's only 1 digits after the decimal. So basically, there is 2 or more um, digits that are basically concealed from us. We can't really tell exactly what is the measurement beyond the 2 digits after the decimal. So in analytical settings, for example, scale number 1 will be always favored because it can give you a really detailed, high reliable measurements. Why that it's helpful? For example, if we talk about THC, which is the active ingredients in cannabis, right? Tetrahydrocannabinoid or cannabinol, 1 to 2.5 milligrams is really enough to kick in the psychoactive effect when it comes to using that material in drugs, right? And medications. So when we say 1 to 2.5 grams, if you convert that, and we will look into conversions, so hang on and try not to be nervous when you see these two decimals, how the 1 gram is now 0.001. We'll do more examples, but take my word for this one. So 1 milligram is equal to 0.001 gram. The 2.5 milligrams, 0.0025 grams. And this is what the balance is going to read. So if I were to take THC and try to measure it in one of those balances, balance number 1 will be favored because it can read all the way down to the 3rd and 4th decimal. The panel balance here, and only the pan balance, can only read to the 2nd decimal. So I can potentially be losing about 1, 2, or 3 milligram because this balance here is concealing the 3rd and the 4th digits after the decimal. Okay? So when you have a small mass that you're trying to measure, this balance is definitely not the way to go, and this balance should be the way to go. Because this will give you a measurement that has a high precision and also does not really cause, for example, a high dose. So if you're trying to design a medication, obviously you don't want to use this balance because you could be manufacturing a medication that has a high dose of THC. Okay. And I'll tell you an example. I also in our lab where I work, we also have we handle and we carry on THC because we use it for our analytical applications. So the DEA, the Drug Enforcement Agency, they show up. Those folks, they show up at least every 3 months, every 6 months, and try to calculate and measure out our inventory. So when I'm trying to measure out the THC in our daily use in the lab, I need to make sure I'm using a high precision scale, right? Because I don't want to make sure, I want to make sure that I'm not losing some of those materials. Because if the DA officer shows up and I show him this balance that I'm measuring, that I'm using to measure my daily use for THC, I could be suspended, and my license could be suspended because I could be wasting, many milligrams of THC because my balance here is not giving a reliable result. So a scale with a high precision is always favored in this case. Okay, let's talk about significant figures now. And this is how significant figures is actually related when it comes to reporting numbers. Okay, so that those numbers that we just looked at the scale, we need to make sure that we're applying the significant figures. So the numbers that I'm reporting either on my data sheet, for example, or my lab report, these numbers actually mean something. And I'm not just putting numbers or coming up with numbers that the measuring device is incapable of measuring. So why is it important to talk about significant figures? Because it is, as a scientist, it is a priority for you to be honest and also to be accurate when you're trying to report a measurement. So you're not reporting more accurate than what the equipment itself can actually measures, or the equipment itself actually allows to measure. We can achieve this by controlling our significant figures. So that's why the scientists report all the certain digits, and one estimated, we call that one as the uncertainty digits. Why is a significant why is what is significant figures? So the number of significant figures is in a result is simply the number of figures that are known with some degree of reliability. Why do we bother do the scientific figures? Because we don't want to report a value with a greater precision than the precision of the measuring device itself. I think that's pretty intuitive, right? If your device measures with four decimals, you need to make sure that you're not reporting 5 decimals or 6 decimals, right? I think that makes total sense. So how do I determine and how do I tell what is my uncertainty for my measuring device? Let's start with the graduated cylinder because you guys will be seeing the graduated cylinder quite frequently in the lab, and we will use that one obviously to measure volume of a liquid, because in many times you will see in your lab procedure, I will ask you to measure a specific amount of a volume in order to conduct a specific experiment. So in this case, if you're trying to really look at the graduated cylinder and see what is my uncertainty in this case, so what we will do is you will basically you would compare the position of the bottom of the meniscus. So we will be targeting the bottom of the meniscus, and we'll try to read exactly where the meniscus is sitting. So when we look at this one, there is 8 and 9 mils, correct? And the 8 and 9 mils, it is subdivided also to 10 different marks. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marks, in every single graduated mark in here, there's a 0.1 ml. So it's 8.1, 8.2, 8.3, so on and so forth, 8.9, and then you go to 9 mils. So when I'm trying to read this meniscus right here, I can say with a high degree of reliability, since it's sitting between 8 and 9, it has not touched the 9 mark, then it is going to be an 8 mils, correct? So my 8 mil in this case is my certain digit because I'm certain it is 8 ml. All right, let's look next now. So the meniscus, it's now 5, 6, 7, right? It has not touched the 8. So I can't really say 8.8 because it's not at the 8.8, but I can say confidently it is 8.7, correct? Because it is somewhere between the 8 and the 7. So I can still consider my 7 my certain digit. So it's 8.7. Now, because it's not really resting on the 7, it's somewhere between the 7 and the 8, my last digit here will be considered my uncertainty because I could see this as 8.74. Someone could see it as 8.75. Someone could see it 8.73. So that is considered my uncertainty. So my uncertainty for a device like the graduate center, in this case, it's 8. It's 0. Oh, I'm sorry. It's 0.01 plus minus ml, right? Because the 4 here, it can be either 3, it can be either 5, and so on and so forth. So the number it varies by a mark of 0.01, either plus or minus. Okay? So that's how to determine the uncertainty in this case. If the meniscus is sitting right on number 8, that still does not change anything of the uncertainty, right? Because the device has not changed, so the uncertainty remains 0.01. Now, with a digital readout, it's obviously a lot easier than the analog or the manual, like reading a ruler, for example, or the graduated cylinder in our previous case. When it comes to the digital readout, your last digit here is always your uncertainty. So in this case, it's going to be 0, 1, 2. So it's going to be 0.123 plus minus gram. So this is going to be my uncertainty in this case. The 5 here, even if you look at the scale, you will see the 5 actually goes up and goes down, because what the balance is trying to do is trying to estimate that last measurement, just like how we did with the graduated cylinder earlier. So the 5 here, everything here you can report with a high degree of reliability and certainty, except for the 5 here. This can vary, and you will see even at the end, the 5 can always fluctuate between 5.4, between 4 and 3, and possibly go down to 2, and up and down. Okay, so your uncertainty will be 0, 0, 0, 1 gram, plus minus. So for given measurements, let's look more details in significant figures, and we also let's look into rules, and we can also how can we use significant figures in mathematical operations. So significant figures, you might also see them referred to as sig figs, or S, F, in different ways in different textbooks. But in general, let's all agree on calling it as sig figs, at least in our course. Okay, so these are the digits that actually carries a meaning. So if there is a 0 or there's a number really doesn't mean anything, we try not to report that number, or really not consider it as significant. Or you can also consider it as insignificant, of course. So leading zeros after a decimal point and trailing zeros before a decimal point. These will be considered as insignificant zeros. So we don't report these as significant figures. Okay. Let's look more into into these rules. So all non-zero digits are significant figures. So I think that's a pretty easy one. So when you get a number and you're trying to calculate your significant figures, simply ask yourself a question: do I have any zeros? If you see there is no zeros, that should be an easy peasy call, right? Because you can just count all those as significant figures. So as you see here as 1.234, there is no significant figures. There is no zeros. So this will be counted as 4 sig figs. The 1.2 below it, same deal. I don't see any zeros. I don't have to deal with anything else. I don't have to count and be worried about significant zeros and insignificant zeros. So the 1.2 grams will be 2 significant figures. All right, now let's talk about zeros, and this is where things start getting a little bit dicey. So zeros between non-zero digits will be counted as sig figs, okay? So the 1002, the zeros between the 2 and the 1 will be counted as sig figs. So the 1002 will be considered for significant figures number. 3.07 ml. Okay, I have a 0. Does it fall between two numbers? The answer is yes. So that will be 3 sig figs. Okay. All right, let's look into more zeros rules. So leading zeros to the left of the first non-zero digits are not considered significant figures. What does that mean? if you look at the 0.001, all these zeros to the left of the 1 will not be counted as sig figs. And in this case, the 0.001 will be considered as a one significant figure number because all the zeros to the left of a non-zero digits will not be counted. Same deal with 0.012. All the zeros to the left of the 1 will not be counted as significant figures. Please pay attention to this. And only the 1 and 2 will be counted as significant figures. Trailing zeros to the right of the decimal will be counted as significant figures. So the 0.0230 will be counted as a 3 significant figures. Now, which number are we talking about? We're talking about this number here. So it is trailing zeros to the right of the decimal point in a number, right? Trailing zeros to the right of a decimal point in a number are significant. So this is to the right of the decimal, right? There is a number here. So this will count as significant figure. Same deal with 0.2 grams. The 0 here will count as significant figure because it is to the right of the decimal following a number. When number ends with a 0 and it's not a decimal point, it's not going to count as significant figure. It will not be considered as sig figures. Like 190, the 0 here, this will not be counted as significant figure. Same thing here with the 2 zeros with the 50,600. So in this case, the 50,600 will be counted as 3 significant figures only. Okay, let's look into some examples. Okay, number 1. How many significant figures do I have in 37.76? Now, obviously, you see the number. It is 4 significant figures, but why? Ask yourself the first question. Do I have any zeros? No. Then they all will count as sig figs. Same thing with number 2. Do I have any zeros? No. Then everything will count as significant figures. All right, let's look at the next one. Do I have any zeros? Yes, I do have zeros. I have the first one, which is the 104, the 0 right here. Okay, so this one, because it falls between 2 non-zero numbers, this will count as significant figure. So I have 1, 2, 3, 4, 5. What about this 0 here? This will count as significant figure because it has fallen to the right of the decimal. Just like how I said earlier. I'm sorry about this. Let's look at this one, number 4. How many significant figures I have? I have only 2. Why? Because this 0 here has fallen to the left of the decimal, so it's not going to count as significant figure. Number 5, no zeros, all significant figures. All right, 600.0. The zeros to the left of the decimal will count as significant figures because I have a number leading here, correct? So 6, 1, 2, these are 3 significant figures. Does this count as significant figure? Yes, because it has fallen to the right of the decimal. So zeros to the left of the decimal will not count as sig figs unless if they were preceded by a number, okay? Or they were trailing a number. Let's look at this one. How many significant figures I have in this? I have only 2 significant figures because all these I have, this is not going to count as significant figures, and same thing with these 2. 0.556, this will count as 3 significant figures, right? Because the 0 here to the left will not be counted as significant figures. This one here, the 400, right? The zeros are trailing, so this will be counted as 1 significant figures because the zeros will not count as significant figure. The 5.000, the 5, obviously, it's a non-zero, so will count as sig fig, and all these zeros will count as sig figs because they have fallen to the right of the decimal. So this will be 4 significant figures. So rounding up and sometimes also rounding down can be helpful when trying to do some measurements. And when you do rounding, what you do is basically you start with the leftmost non-zero digit. So which number am I talking about? Example, so we're talking about the 1, for instance, in 130. So you will round this one up or round it down. Or the 6 in this case, the most non-zero. You will keep n digits and replace the rest with zeros. You will round up if if it is doable, or you will just let it rest and not do anything and change it. Now, what determines this? The number adjacent to the number that you're trying to round up or let it rest will really determine this. So in this case, if we're looking at the 3, for instance, the 3 is below 5, so the 6 will remain the same. So you're not going to round this one up. It will be 0.06. If the 3 were to be 5 or more, then the 6 will have to be rounded up. So it will be 0.07. Let's look at this example here. So if rounding 0.039 to one significant digit, the result will be 0.04. Why? Because you will look to the leftmost non-zero, which is the 3. So this is the number that we're trying to round. Then I will look to the number adjacent to it, next to it. Okay, number 9. Is it 5 or more, or is it below 5? It is obviously 5. It's more than 5 because it's a 9. So then the 3 will be 0.04. So I round up. If, for instance, the number was 0.033, so the number next to the 3 is a 3. It's below 5. So you're not going to round this one up. Rather, the number will remain the same, 0.3. That's basically what round up means. I think it's pretty easy. All right, let's use significant figures in calculations. So for addition and subtractions, we have actually two set of rules for addition, subtractions, and also for multiplications and divisions. So for addition and subtraction, the result, your answer should have as many decimal places as the number in the calculation with the smallest number of decimal places. And I want you to pay attention to this keyword, smallest number of decimal places. That's for addition and subtraction. When it comes to multiplication and division, the result or your answer should have as many significant digits as the number in the calculation with the smallest number of significant figures, significant digits. Remember, significant figures and decimal places. So these are the two differences when you're doing mathematical calculations, addition, subtractions, multiplication, and division. All right, let's do some examples. So let's do the first one, the 37.76, 3.907, and 226.4. So as you see, this is an addition operation, correct? So what we are trying to do here, or what we will need to calculate, we'll need to make sure that our final answer should have the same number of decimal places as the number with the smallest number of decimals in the numbers that I'm trying to calculate. All right, so let's count our number of decimals. How many decimals in the first one number here? There's 2 decimals, right? 1 and 2. We're not talking about significant figures. How many decimals I have here? 1, 2, 3. How many decimals I have here? I have 1. So I have 2 decimals, I have 3 decimals, and I have 1 decimal. So my final answer should have 1 decimal at the end, and that's exactly what I have here. So if you were to crunch in this number now in the calculator, you will get a number would look like this, 268.067. But the number that I have here is 268.1, because I will have to report 1 decimal, only one decimal digit after the decimal. But because I have a 0, I'll have to also look at the number next to the 0. And as you see here, this is the number 6. And it's more than 5, correct? So in this case, I will have to round up. So the 0 here will have to go up by 1 digit. So the 0 will turn into a 1. So the final answer would look like 268.1, because the 0 was rounded up to an additional digit due to 6 that was adjacent to the 0 more than 5 or more. So we rounded up. Okay? All right, let's look at the next one. So the next one is a subtraction. So I'll be calculating my decimals. 2 decimals on this, 3 decimals on this. So 2 versus 3. So my answer should have 2 decimals, right? Not 3 decimals, 2 decimals. Okay, sorry about this. So if you were to crunch in this number now, again, also in the calculator, these two numbers, and do this subtraction, the number that you will be getting, it will look like this: 286. 286, sorry about that. 5, 3, 6. How many numbers I need to report? 2 decimals. So my number would be all the way down to 286.53 to the 3. But before I do so, I'll need to look to the number next to the 3. Is it more than 5? Is it 5? Is it less than 5? It is 5 or more. It is a 6. So the 3 will have to round up to 4. So my final number would look like 286.54 because I rounded the 3 into the next digit. Please pay attention to this. All right, let's look at the next one. This is another addition operation. So when I do this, I'll have to count my decimals. 1, 2, 3. The 0 will count as a decimal. This is not significant figures, guys. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2. So I have 3, I have 5, and I have 2. So my final answer ought to have 2 decimal digits, not more than 2 decimals. All right, so let's put this number in the calculator. The number would look like this: 132.323. I'm reporting how many decimals? 2. So this is my number I'll be reporting. But before I do so, I'll have to look next to the number, to the last number that I'm reporting. Is it 5 or more, or is it less than 5? It is less than 5. It is a 3. So the 2 here is not going to be rounded up. Rather, it will be just remain the same. So it will just rest, or let it rest. So the number will be 132.32. So that's where the 2 is coming from. All right, let's do one last one in addition subtraction before we transition into multiplication, division, and some, I call these combo problems, where you have a combination of subtraction and also subtraction, addition, and also multiplications. Okay? So let's do the 125. So if you were to do this one on the calculator, 125 minus 0.23 plus 4.109. The number that you'll be getting, it would look like this: 128. I'm sorry about that. 0.87. All right, let's delete all this. Clear off. Okay, here we go. So the number would be 128.879. Oops. 179. Okay. What is the number that I have here? Is 129. Why do I have 129? Because I have 125. How many decimals I have on the 125? I have 0 decimals. How many decimals I have on the 0.23? I have 2. So I have 0, I have 2, and I have 3. So my final answer shouldn't have any decimals because I have the 125 that doesn't have any decimals. So as I said earlier, if you put this number in the calculator, it would look like 128.879. I can only report the 128. I can't report beyond the 128. But because 8 after the decimal is more than 5 or more, the 128 can be rounded to 129. So my final answer will be 129. Okay? So that's in terms of addition and subtraction. Please pay attention to the decimals, and then count your decimals. And then once you do your calculations on the calculator, try to conform to the rule of decimals and factor and consider in rounding up or not doing the round up, basically. Okay, let's do some multiplication and division and see how the significant figures here will be counted. Um, so on number one, obviously my answer is 5.1, but let's see how we ended up with a 5.1. Since it's a multiplication, then what I need to do is I'll need to calculate my significant figures, not my decimals. So now, what is my number of significant figures on this one? That's a 3, right? Because there's 1, 2, 3. All non-zero numbers will be counted as significant figures, and the 0 between the two non-zero numbers will also be counted as significant figures. So I have 3 significant figures. On this one here, I have 2 significant figures, right? Because they're all non-zero numbers. So my final answer has to have nothing more than 2 significant figures. All right, so let's put this number in the calculator. If I were to multiply these two numbers in the calculator, the number that you'll be getting, 5.05. Right? So this is the number that we're getting on the calculator. But I can't use this number. The reason why, because this number is 3 significant figures, right? And I have 2 significant figures. So I have my number, my final answer has to have 2 significant figures. So I can only report down to here. But I can't do this because I'll have to round this up due to the 5 being 5 or more. So my answer will be 5.1. And this is 2 significant figures. So let's do now the 600, or number 2, divided by the 5.2302. So first, let's count our significant figures. How many significant figures I have on this guy here? The 600, I have 4 significant figures. Why? Go back and read the rules, right? Because 1, 2, 3 zeros will count as sig figs because I have a non-zero number coming ahead of them, right? So will be 1, 2, 3, 4 sig figs. This one here will have 5 sig figs. So my final answer should have 4 significant figures. Now let's do this number in the calculator. The number I'll be getting is 114.718. And I can only report 4 significant figures. So it's going to be 114.7. I'm not going to round the 7 because 1 is less than 5. Let's do this multiplication. How many significant figures I have on this one? I have 1, so this one has 2 significant figures, right? How many significant figures I have on the 273? This one has 3 significant figures. So how many total significant figures I should have in my final answer? I should have only 2 significant figures, right? I can't have 3 because the 0 to the left of the decimal is not going to count as sig fig. So now if I were to put this number on the calculator, the number I'll be getting is 0.8736. But I can only report down to here, and the 7 here is not going to be rounded up because the 3 is less than 5, so it's 0.87. All right, let's do these this combination problem where you have multiplication as well as addition or subtraction. In this case, is subtraction. So in this case, well, what do I follow? Do I follow the significant figures count, or do I follow the decimals? You'll follow the significant figures. Okay, so the multiplication and the division, they will always supersede when it comes to the rules of significant figures versus decimals. So in this case, if you have a multiplication and you have subtraction, significant figures will have to be considered in the final answer and not decimal places. So in this case, what you need to do is what we have been talking about. Count your significant figures. So in this case, I have 3. In this case, I have 1, right? In this case, I have 3 with a 32. So my final answer should have only 1 significant figure. Now, if you were to do this operation now on your calculator, you'll get something like 4.17. But I can only report the 4, right? Because I can only have 1 significant figure. So hypothetically speaking, if my answer was 4.67, again, hypothetically speaking, I can only report the 4, right? But because the 6 is more than 5, then I'll have to report 5. So I'll have to always think of, rounding up and look at the number next to the number that you're trying, the last number that you're trying to report. Okay. This last one here, it's a little bit complicated and also involves the scientific notation, which is something that we have not talked about yet. It's actually coming up on the next slide or so. And you shouldn't expect this on the exam. I'm going to try to make it even easier on the exam. So, but it's a good thing to practice on these problems, so you become even more familiar with scientific notations and also doing the round up, and also obviously calculating your significant figures. So in this case, I have a multiplication, so I'll have to count my sig figs, correct? So how many significant figures I have on this one? 1, 2, 3 significant figures, right? Okay. Oops, no, it's actually a 2 significant figures, right? So this one is a 2 significant figures. 1, 2. The 0 will not count as significant figure. So how many significant figures I have on this? This one has a 3 significant figures because the zeros to the right of the decimal will be counted. So I have 2, and I have 3. So my final answer should have 2 sig figs. Now, if you were to multiply this in the calculator, you'll get 1350. How many significant figures I have? 1, 2, 3. Well, this one then is not going to work. I'll have to report this number or display this number in the way that conforms to the scientific figure rules, right? So the 1350, what I can do, I can round this up to 1400, right? Because I can round the 3 to 4 because the 5 is 5 or more. So the 1350, it can turn into 1400. And this one is actually 2 significant figures. So this one now conforms and agrees to the rule of significant figures. Or you can also convert that into scientific notation because the 1400 also equals 1/4 times 10 to the power 2. We'll talk about scientific notations in a minute. Please try to do as many practice problems on this one. You will have a homework assignment for chapter 1, obviously, and yes, it will have some practice problems on these. Try to be familiar with those. I think the book also has some examples if you want to get more. If you want to get even more examples, let me know and I'll be more than happy to assist you with some. But these will be on the first exam, that's for sure, and I probably will have a good portion of the first exam. So try to practice and be familiar with this. And don't say I didn't say so. So let's talk about scientific notation. And the method of scientific notation really helps us, especially later on in the semester when we're talking about the mass or the diameter of the atom. We're talking about the mass of the electron, as we saw earlier several slides ago when it was 10 to the power negative 28. I can't even imagine trying to write all these zeros and try to display those numbers using the decimal. I think it will be pretty unreasonable and also kind of ridiculous to try to write that on a piece of paper. So what we use the scientific notation because it helps us present numbers in a more abbreviated fashion, easy to understand also. So for example, if you look at the first number that you see on this slide, which is 3 times 10 to the power 8, but what you see here is 300 million basically. So this is the speed of light. But if you look in any text, any science textbooks, you will never see the number reported in this way. It's always reported in a scientific notation way method because that would make more sense. Maybe the 300 million you can probably, I mean, if you want to write it down, it's probably inconvenient, but you can still write it down. But can you imagine a mass of a dust particle? You'll be sitting and counting zeros all day long, trying to make sure that you are basically writing down the correct number. So that's why we use the scientific notation. It also prevents error and also displays the number in an easier way. So scientists have developed a shorter method to express very large number. This method is called the scientific notation. The scientific notation is based on power of the base of number 10. So we will use the number 10 and we will put numbers on top of the number 10 or the powers in 10 to replace the zeros on these fractions or on those decimals or in those on these big large numbers. So how do you do this? Well, here you go. You put the decimal after the first digit and it dropped all the zeros. In this case, like in this number, in this large 233 billion, as you see here with 9 zeros, what you do is you drop the decimal right after the 2. Okay, right here. And then you just count your zero. You count your digits. How many digits did you move, or how many digits are you trying to abbreviate? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have moved the decimal 11 spaces or 11 spots. So then you'll have to substitute those 11 movements with number 11 on top of the 10. And this will be a positive 11 because later on we'll have negative numbers. So this will be 2.3 times 10 to the power 11. The 11 here replaces the 11 places that you just moved the decimal all the way down to the 2. Okay, so which way is easier, writing 2.3 times 10 to the power 11, or you do want to write 234 with 9 zeros ahead of it? I would take this one any day of the week. Okay, I'm pretty sure you do too. So if the number is less than 1, so this is in a case if the number is larger than 1. In case if you are confused and you're like, okay, so do I put a negative 1 or positive 1, positive 11 or negative 11? Ask yourself, is the number larger than 1 or less than 1? If it is more than 1, it's going to be a positive power over the 10. If it is less than 1, it is going to be a negative power over the 10. Plain and simple. So let's look at this number here. So you'll put the decimal after the first digit and a drop the 0. So you'll do essentially the same thing. I'll put my decimal right in here. And then I'll cut, and then I'll count my decimals. Same thing, if you count all the way down to the 2, you'll see yourself that you actually move the decimal 11 spots. So this 11 will have to be substituted with 11 with 10 with the power 11. But in this case, it's going to be a negative 11. Okay, because the number is less than a 0, 11 places. All right, let's do some examples. 1,000, same thing. So what I will do is I'll move the decimal right in here. So how many digits did I move? 1, 2, 3. So it's going to be 1 times 10 to the power 3. So the 3 here represents the 3 places that you just moved the decimal to. Let's do this large number here again. So what I will do is I'm going to drop the period down here. The last number that I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I just moved 10 spots. So it's going to be 1.456 times 10 to the power positive 10, right? Because I moved 10 spots. Let's do this one here. So I'll do the decimal right in here. So I'll move 1. I moved 1, 2. So it's going to be 3.89 times 10 to the power negative 2. Why is it a negative 2? Because the number is less than 1. All right, I have the decimal here. So I'll move it all the way down here. So I'll be moving 1, 2, 3, 4. So how many slots did I move? I moved 4 slots, correct? So it's going to be 3 times to the power negative 4. Negative 4. Please make sure to use the positive and the negative. You don't have to write the positive, but at least you have to write the negative if the number is less than 0. If you don't, your scientific notation will be wrong, and you won't be getting any credit for this. All right, let's do the 12 here, or the 1.2, our last example. So I'll move the decimal to the last number, which is the 1. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's where my decimal is. So I moved 10 spaces, so it's going to be 1.2 times 10 to the power 9, or positive 9, because the number is larger than 1. Okay. I think this takes care of everything on chapter 1. The next few slides that I have here is for you, how to use the scientific calculator and how to use the specifically the scientific notation. So if you have a calculator, please try to use these slides. These could be a little bit helpful, especially during the exam, because we will be dealing with large numbers in the lab, as well as as well as the lecture. So please be familiar with how to use the scientific notation in your calculator. If you don't have a calculator yet, please get one because you'll need it. Okay? Thank you so much.